Yeah.
Okay.
Okay. The story of countercurrent chromatography actually began over 2,000 years ago with the invention by Archimedes of the Archimedean screw, or Archimedes pump. And I'll pass around for you to look at this small model of an Archimedes pump. And what he found was that if he made a coil, what we would say a coil of tubing, and put it at an angle and then immersed the bottom part in water, when he turned it in this way, each loop of the screw would half fill with water, and it would pass the water up and it would be discharged from the upper part of the coil. Now, it would make a difference in turning this which way the coil is wound. It could be wound clockwise or counterclockwise. However, counterclockwise and clockwise are ambiguous terms when it comes to describing aspects of countercurrent chromatography because they depend upon which end of the device you're facing. And so Ito, when he later developed the technology, used another means, and he called the ends of the coil the head and the tail. And you'll see in this small model on the bottom, you'll find in the tubing a very small bead. And if you turn it in the direction indicated on the side of the model, you'll see that the bead progresses with each turn, one loop up to the top of the coil. And the coil, the end to which the bead moves, is called the head. Now, if you wound the coil in the opposite handedness, then it would move in the other direction. So it's much better, wherever it's possible, to describe the handedness of the coils by head and tail rather than right and left-handed. And I'll pass this around for you to look at. There are modern uses of that Archimedes screw. It never did go out of date. And in the lecture, I'll actually show another picture of a modern one. Now, preceding countercurrent chromatography, there was a technology called countercurrent distribution. And the name, actually, countercurrent chromatography, Ito assigned by analogy to countercurrent distribution. That was invented by Lyman Craig back in the 40s, at the time, actually, during World War II. And this is a small model of what that apparatus looked like, and it consisted of in the first model, two stainless steel pieces, which had a very closely machined interface. And if you look at it, take it apart and look at it, you'll see that there are holes drilled. This particular one has 6 holes. The first model that he made, I believe it was larger than this and had 19 holes. And you'll see that you could fill the bottom holes here with it disassembled this way with the lower phase, let's say chloroform, and then you could put the top on, and there were means of holding it tight, and you could then fill the upper part with a lighter phase, in this case, let's say water. And then you could shake the apparatus. There was a means of shaking it this way. And then your sample was put into the first tube, which he called the zero tube. And when you shake it back and forth, the sample would distribute between the 2 phases. And then you would slip the apparatus over one tube in this way, and that would move the upper phase over one step, and the lower phase would remain. And then you would shake and equilibrate again until it came to equilibrium, and then you would shift it again, and you would continue that until you got to the last tube. And then that was called the fundamental distribution. Now, you could continue it, and they did figure out ways of doing that, so as to get an eluted phase, and that becomes a little bit of analogous to chromatography. However, the two techniques are fundamentally totally different, in that this apparatus is actually an equilibrium apparatus. You do mix this until the two phases are in equilibrium, then you shift it to the next tube. Whereas in chromatography, you have a dynamic situation where you don't actually necessarily reach equilibrium. It depends on a number of factors, and we measure something equivalent to these tubes, which we call a theoretical plate. But they are fundamentally different techniques, even though one can model the other. Now, the reason for the name, Craig called this countercurrent distribution, and even though only one phase moved and the other phase remained stationary. And his argument for the name countercurrent was that it didn't matter which phase you were in. If you were in one of the phases, you wouldn't know which phase moved, and so in effect you do have a countercurrent separation. Historically it proved to be a bad name. There was a lot of controversy over it, but it remained until this day, and it's not likely to change. Now, Ito, when he invented countercurrent distribution, countercurrent chromatography, actually adapted the name from this because it was a similar situation. You had one liquid phase remaining stationary and then another liquid phase which passed over it. And so it was completely analogous to this. And again, controversy has broken out over the name. But now, one of the early instruments that became moderately successful was called what is now called the Type I coil planet centrifuge. These instruments are all what are called coil planet centrifuges in the sense that there is a coil which is mounted, as we would think, on a planet, on an axis, which revolves around a central axis, or solar axis, if you like. And so it does revolve as a planet. And I have a model here which shows how that happens. And this one is the type, what we now call the Type I instrument, which was driven by a pulley. And the pulley caused the planet to rotate, and usually it's said that it rotates once in each orbit, but if you look at it carefully, you may not agree with that, but I'll explain in detail later why it's said to be one rotation on its axis in each orbit rather than two. If you look at it, you will conclude it's two. Now, this is a visually projectable model of the Type I machine, and you see a series of coils. These would be in an eccentric configuration, and they move around a stationary pulley in the front, and that pulley there moves the coils. And if you look, you will see the coil going around in that fashion. And I think you probably would agree with me, that isn't rotating on its own axis at all. If you look at the dot, it's in the upper circle and stays there. So my opinion of it, looking at it here, is that it's gyrating around a central point. It's not actually rotating on its axis. Now, if you read the literature on CCC, you'll find that it tells you that this rotates once on its axis as it goes around the circle. And as we go through this, you'll see why that is so. And it's true, except they're not giving the real reason for the once rather than zero. Now, it's interesting to see how this point actually moves as it goes around the circle. Let me show you that first. And to see that, I'll put this on, which doesn't show the coils, but it shows points at different distances from the planet. And in the actual lecture, I may have explained this earlier, that these numbers here are referred to as beta, and they are the ratio of the distance from the planet axis to the point divided by the distance from the solar or central axis to the planet axis, and that is called beta. And it's important to realize that because there are vast differences between this eye machine and another machine that I'll describe later. Now, this slide is rather complex, but if I put beneath the image that you see there, I've put an image of circles underneath this, and what you'll see is that, let's look first at just this point, the red one, at 0.85 beta. And I may not have them aligned perfectly, but you'll be able to see the sense of what I'm saying. As I move it now, what you see is that that red point follows this dotted red circle as it goes around the orbit, like that. Now, I made another red point also on this same beta range. This is also 0.85, but it's on a different position on the particular set of coils. And if you watch it, it's going around this circle. And if you take other points, I put other points here at other beta. Here's one at 0.5 beta, here's one at 0.25 beta. This one follows the green circle, this one follows the orange circle. So the point that I'm trying to make here is that no matter where you put the point, it follows a circular path, which is actually the same radius as the radius r, the same as the distance from the solar axis to the planet axis. Now, because of the circular motion, you get a centrifugal force field formed. Now, it's not the same as a simple field in a centrifuge. It's, in fact, you'll see it's a very peculiar field, but, and this I've made the field cover a much bigger area than is necessary here. But what you see is that the field is a series of parallel vectors which all have the same strength. And if this were 10 centimeters from planet to solar point, and if you were going at 800 RPM, this would be equal to 72 times gravity. It doesn't matter where it is. They're all 72 times gravity. And now watch as those points go around, and you see what really is happening. Now, the circle, or the columns, if you view these as coils, now it is making one rotation on its axis relative to the centrifugal force field. And so in doing what's called the kinematic analysis of this system, the fact that it's rotating once relative to the force field, or you could say relative to the sun. If you stood on the solar point and watched, you would see it's going around once. And if you, but if you stand outside the system like I am, then you're going to say it's not moving at all. But because the solar field is moving, it's going around with the apparatus. And so the important feature is its movement relative to the vector field. Now, this vector field is very complicated. Let me put back on the other overhead that I just had, which shows actual coils, and put the field on again. Now you see the same thing, but with the coil in place there. And now you see clearly it's rotating with respect to the force field. Now the trouble is you can't follow exactly here what is happening with respect to a particular coil, because the way I've represented the force field, I just arbitrarily drew these lines in different places. But if instead we draw the force field relative to the coil, and to do that I had to make another special device here, which I hope works. And here we see one of those coils. I made it a little bigger so that you could see it better. And now you see 4 points on the coil, and you see the force field on each of those points. Now this is complicated to represent, so I have to help it show the image that I want. And as this goes around, the force field is going to follow the central arm there, like that. And it's going to stay parallel to the central arm, but you see the coil is rotating relative to that force field. And so in effect, you have a force field that's staying in sync with the arm there as it goes around. It's pointing now in the direction that the other force field was, but now you see the vectors are staying in the position that I first placed them on the coil. Now this is very analogous to the situation where you would have a coil rotating in a solar, or in an Earth's gravitational field. Let's say that was the Earth's gravitational field and we rotated the coil. That's the same thing as what we're seeing here. Almost. Not quite, because the weirdness about this particular force field is that all the vectors are parallel to one another, and they remain parallel to one another as this rotates. Now, that feature doesn't change as we increase the speed of rotation. The vectors get stronger, but they still remain parallel to one another. That's not the case with the Earth's field. If you rotate a coil in the Earth's field, the coil itself generates a force field, and that causes a distortion of the vectors. So, but it's similar in the sense that the vectors always point in the same direction, and the coil rotates through it. So it's very interesting in that respect. Now you can also see another feature. I'm not sure I can demonstrate this quite as well, and I may not have made the optimum drawing for this. But here's a similar drawing to what I just gave you. But let me see. Here. And now I've got those same vectors there. But now I put two phases in the coil. And one is the red phase, which is the heavy phase, and the yellow phase, which is the lighter phase. And now, as the coil goes around, I forget which way I was rotating it before, but as the coil goes around, you'll see the phases kind of stay in the same place, and they flow over one another. And you can see that this is the reason why you get what's called cascade flow. You form like a waterfall as it goes around. But That's the kind of thing you get at slow rate of speed with a gravitational field as well. Now there's another feature I should have pointed out too, and that is if I rotate this in this direction like that, and you look at the, I'll put the force field back to make sure you see it. All right, now as I rotate this, the other thing to notice is that is rotating once with respect to the force field, but it's rotating in the opposite direction to the direction that the frame of the machine or the vector field is moving. So it's moving once in each orbit, moving around its axis once in each orbit, but in the opposite direction from the direction of the machine itself. Now this machine, the I machine, and the next one that I'll describe, called the type J machine, are said to be synchronous. And the reason they're called to be synchronous is that each one rotates once in its orbit around the solar axis. However, that unless you represent the force field in this way, it's very difficult to see that, because it's really synchronous because each does rotate once with respect to the force field. The I machine rotates in the opposite direction from the force field rotation. However, the J machine rotates in the same direction. So they do rotate each of them once, but in opposite directions relative to the force field. Now, the last setup they described was the so-called type I machine. And Ito had developed that through almost 1980. In the 1970s, he developed that. I'll point out later that the stationary phase retention in the system is a very important feature of countercurrent chromatography. And it would be better if the stationary phase retention is very high. But it turned out that with the type I coil, the retention was not that great. Sometimes it would approach 50%, but not often go beyond that, and sometimes it was much lower. So he was looking for other features. And another feature that is important about these, and I did forget to mention it with regard to the type I coil previously, but if you look at the coil going around, the leads going in and out of the coil do not twist. And that's why I said it doesn't rotate as it goes around in the orbit. And of course, if it doesn't rotate, it doesn't twist the leads going in and out. So that was an important feature, and the first time that Ito had made